Hello everyone, I'm going to be talking about counterfoil, a technique to verify provenance of integrated circuits by authenticating chip packages. I would like to acknowledge my co-authors for their support and also NSF for funding this project. To fit into a 10-minute format, this talk will be at a fairly high level and hopefully will entice you to read the paper for more details. Around $5 billion are lost each year in the semiconductor industry due to counterfeits. Counterfoil is our scheme to verify IC provenance and help prevent counterfeits. Here is the global view of the semiconductor distribution. Millions of chips are manufactured in a reputable foundry somewhere in the world. In another part of the world, a consumer orders chips online. Chips travel from the manufacturer to the consumer through a network of resellers, shippers, and wholesalers. The complex nature of the distribution network provides many places for counterfeit devices to sneak in. So, our work is not about stopping nation-state attackers, but it is instead aimed at stopping ordinary profit-seeking counterfeiters that remark chip models, recycle old chips, and sell them as new, or regrade chips to sell them at a higher cost. The counterfeit chips can find their way into distribution channels, and so the consumer that ordered the chips doesn't really have a way to know whether the received chips are from the counterfeiter or are they from the reputed manufacturer. Most people don't think about this when ordering chips online, but counterfeits are indeed a real problem for government, defense, hobbyists, and so forth. What approaches do people use to prevent counterfeit ICs? One approach is anomaly detection, where you look for something unusual that is uncharacteristic of a legitimate chip. Examples include visual inspection, classification using neural networks, or the use of electronic signatures. The second approach is to authenticate provenance, where you look for something that you trust. Often, the trusted thing involves a package of the chip. For example, DARPA Shield uses a secure wireless dial-up that is embedded in the package for authentication. A company called Applied DNA Sciences tags chip packages with plant DNA to help with authentication. So if we look close enough, biometric signatures exist all around us. Even blank paper has surface texture which can be used for provenance of important documents. So in plastic packages, surface texture could potentially be used as a biometric signature. This is the basis for counterfoil. So let's look at how ICs are packaged. They go through a process called transfer molding, where the bare IC die sits on a lead frame inside a mold cavity. Liquefied molding compound is made to flow through the cavity and cure around the die to form a plastic package. The surface texture comes mainly from the roughness of the mold, amongst other sources. So in our scheme, the manufacturer reads a fingerprint from the surface texture of the package and makes a record of it. The chip is then released into the untrusted distribution channel. The consumer later reads the fingerprint from the received chip and compares it to the record for authentication. Here is the protocol. The trusted manufacturer tags each chip with an ID label and creates a digitally signed fingerprint during the enrollment phase. The consumer later verifies that the digital signature is valid and that the enrolled fingerprint matches the chip package that was received by the verifier. So here is our attack model. Again, we seek a profit. We consider a profit-seeking counterfeiter. Because the attacker cannot obtain the private key of the enroller, he cannot sign his own fingerprints. Because the fingerprints are bound to a chip instance, swapping the label from one chip to another will not work. And because fingerprints are difficult to forge, the attacker will not be able to create a counterfeit that matches an enrolled record. So far, I've shown the problem of counterfeit ICs and given you a sketch of how we try to foil this with record keeping. So we call the method counterfoil in part because records of authentic chips are reminiscent of counterfoils, which are the stubs that were retained from checks. These are, of course, before the days of Venmo. In the rest of the talk, I will go through some details of how package fingerprints are checked using low-cost equipment and at production speed. Our experimental setup consists of cameras from 2 vendors, and we use 2 different instances for enrollment and verification. Our main dataset comprises 2 chip models packaged in plastic dips, some of them coming from the same mold. And we use OpenCV and Crypto++ for implementation. Our source code is publicly available. A naive way to extract fingerprints is to compare images pixel by pixel for similarity. But this approach is very sensitive to alignment, even with the use of fiducial marks. And brute forcing alignment is impractically slow. So rather than comparing every pixel, we fingerprint based on identifying features or key points. These are detected using computer vision algorithms. Each key point is associated to a position on the chip and a position in a multidimensional feature space. Key point information is recorded for each chip during enrollment. At verification, key points are again extracted from the chip and compared against the enrolled key points. Key point pairs that are closest in feature space are potentially corresponding points in the package surface. So ransack algorithm is used to find geometric correspondence between the key point pairs. Key point pair is considered an inlier based on both feature similarity and also geometric consistency. The number of inliers is our similarity score. In this particular case, we have 4 inliers. The red key point does not fit the geometry that was estimated. So when key points from images of the same chip are matched, we see hundreds of inliers. Our scheme works well with variations in scale and rotation as well. So in a common attack scenario, the counterfeit chips are produced from a different mold. Comparing key points of chips from different molds, almost no inliers are found. So provenance can be established by setting an acceptance threshold for the number of inliers. We see similar results when we repeat this on different chip models. So next we consider a more sophisticated attacker who can potentially forge a mold to match enrolled fingerprint. We model this case by trying to match fingerprints of chips that we know are packaged in the same mold. We know this from the mold marking imprinted on the surface. So from the histograms, there is very little overlap between the same mold and same chip distributions. In the worst case, we have to allow 16% of false positives to achieve a 95% true positive rate. This means even if the attacker creates a perfect mold, he will still be largely unsuccessful due to variability in distribution of filler particles, the curing process, and mold buildup. Counterfoil is a practical scheme with almost no additional equipment cost. We are able to authenticate in 150 millisecond on Intel CPU, so real-time verification on pick-and-place machines is possible. We found that chips can still be matched pretty well after 1 hour inside a rock tumbler. We also tested counterfoil on other package types of varying sizes and material. Authentication works well on plastic packages. Ceramic package shows some promise as well, but the approach does not work on things like metal and wafer level packages that lack surface texture. To summarize, counterfoil uses fingerprints from surface texture of chip packages to verify IC provenance without a chain of custody. We presented an overview of counterfoil as a practical solution to thwart profit-seeking counterfeiters. Please do check out our paper for more